So now, how do computers represent the data? We've been keep talking about the storing the data into the memory, but how does the computer actually store the data onto the memory? As a humans, we understand, we can look at the images and we can interpret what that image has. We can look at the text and symbols and we can understand that. We can basically speak and communicate in different languages. But when it comes to the computers, everything that they see and talk and they understand is all ones and zeros. That means everything is a binary that the computer understands. So if you're trying to store an image or try to process an image or try to process a file which consists of a data or a text, it has to be all converted into the ones and zeros, because computers understand only ones and zeros. That's their language. So if you look at a simple addition operation, which is 1 plus 2 is equal to 3, where we have 4 symbols, which is 1 as a symbol, plus as a symbol, 2 as a symbol, 3 is equal to a symbol, and 3 is a symbol. By looking at this, humans can easily understand and understand and interpret what it is. But if you want, if a human wants to exactly tell the same thing to the computer, that has to be represented in the form of ones and zeros. And if you look at it, that 1 plus 2 is equal to 3 is being converted into ones and zeros. So the symbols, so everything that you see is a symbol. So 1 is a symbol, plus is a symbol, 2 is a symbol, equal to is a symbol, and 3 is a symbol. And every symbol, we call that as an ASCII character, and that is being mapped with the decimal number, which is an ASCII decimal number. That means every character is being given with a number, and that mapping, the symbol to the number mapping is called as an ASCII mapping. And then that ASCII mapping will be further converted into the binary. So if you take 49 as an example, the 49 is being converted into a binary. Don't worry about this at this moment in time. We will, as we keep proceeding in the code, you'll understand how this conversion basically happened. So the important takeaway that you all should understand in this slide is everything that you see is a symbol, and that symbol is being given with a number, which is a decimal number. And that number is further converted into the binary, and that will be stored inside the computer's memory. Then the CPU picks that information from the memory, and it will do all sort of processing that's supposed to be done by the CPU. So, by the way, the ASCII stands for American Standard Code for Information and Interchange, where this is a kind of a mapping which is given by this organization, which is an American standard organization, which is being used to, which has a mapping between each and every symbol that you see on your keyboard with a decimal number. So for say, if you take A as an example, A as an ASCII character, which is being given with the decimal number 65. So that means every character or every symbol on a keyboard that you see will be mapped with the decimal number. And then the decimal number will be further converted into the binary, which looks something like this. The very important thing that you all have to remember is the ASCII character is always a 7-bit representation of a decimal number. So for say, A, which is 65, is being represented in 7-bit, which looks exactly like this. In the same way, whatever the characters that you see on a keyboard, every character will be mapped with the decimal number, then further with the binary number. So now we should need to understand what is a bit, what is a byte, and the decimal number and the binary number system. As we have been keep talking that everything the computer understands is ones and zeros. So to justify that, we need to basically understand this important jargons, which plays a very, very important role. So how do you measure the memory? What are the units of measuring the memory? So if you go to the granular level of the units of a memory, everything has been represented as bytes inside a computer. Now, what is a bit? Bit is nothing but the computer stores the information using the bits. A bit stores either the value 0 or 1. The sequence of 2 bits can represent 4 distinct values, which is 0, 0, 0, 1, 1, 0, and 1, 1. The sequence of 3 bits can be represented with the 2 cube, where you can represent 8 different numbers. So they would be 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, and 1, 0, 0, and 1, 1. Now let's take an example and understand how to represent a decimal number in the binary with 2 bits and 3 bits. The combination of 8 bits represents 1 byte. So 8 bits is equal to 1 byte. So a byte represents the different types of information depending on the context. It might represent a number, a letter, a program instruction, a part of an audio recording, or a pixel in an information. It could be anything. If you go to the lowest granularity of a computer memory unit, what you see is a byte. Most of the modern computers with the byte addressable memory cannot store an individual piece of data that is smaller than a byte. That means most of the computers takes the byte as the granular unit of a memory. So the byte is also the smallest addressable unit of a memory in the most modern computers. So everything computer represents the data in the form of a bytes. Imagine that you have 2 memory locations which looks like this, and in each memory location you can either store 1 or 0. It could be either 1 or 0. So to represent a 0 in these 2 bits, then it looks something like this. It would be 0, 0. The 2-bit representation of the 0 is 0 and 0. Now, if you want to represent 1 in 2 bits, then you have to add plus 1 at the MSB location of it. Now, 0 plus 1 is 1 in binary. And now, this 0 will come as it is. So this is basically the 2-bit representation of 1 in binary. Now, if you wanted to basically represent symbol 2 in binary, then you have to further do plus 1 to it. So in binary addition, when you perform a summation of 1 plus 1, that will result into 0, and it will carry forward a 1 to the next least significant bit. Now you have 1 over here, and then you have a 0. Then you have to perform an addition between the carry forwarded 1 and then the 0. This is basically going to result in 1, 0. The 2-bit representation of a 2 will look like 1 and 0. Now when it comes to the 3, then you have to then you need to further add 1 to the MSB location, which is the most significant bit location. Now when you do this, then 0 plus 1 is going to be 1. There is no carry forward because 0 plus 1 doesn't result any carry forward 1, and this is going to be 1. This 1 come as it is. So the maximum number of decimal numbers that you can basically present in 2-bit is only 3. The maximum number would be the 3, because everything has been now 1 and 1. Now when you further add 1 to the MSB, this will basically result into 0, 0, and there is a carry forward 1, but you do not have bits to store this 1 over here. So that means if anyone asks you, hey, how many decimal numbers I can represent with the number of bits, there is a very simple formula. So you need to take the number of bits, where you need to take that as a power of 2, and then do minus 1. So 2 to the power of 2, because you have 2 bits, now this 2 will be the power of 2, minus 1 is going to give you 3. So that means when you have 2 bits, and if you wanted to represent a decimal number into the binary, the biggest number that you can represent would be 3. Imagine that you have 3 bits. The biggest number that you can represent in this 3 bits would be 2 to the power of 3 minus 1. It's going to be 8 minus 1. It's going to be 7. So that means the maximum number that you can represent in 3-bit would be the 7. So now let's look at how does a 0 looks like in 3 bits. If you take 0, the 0 is going to be 0, 0. Now 1 is going to be plus 1. You have to do a plus 1 over here. So the resultant is going to be 1, and these zeros will come as it is. Now if you take 2, then you have to do further plus 1. This is going to be in binary addition. 1 plus 1 will be 0, and there will be a carry forward of 1 that goes to the next least significant bit. Then 1 plus 0 is going to be 1, and this 0 will come as it is to the down. In the same way, you take 3, that will be represented as 0, 1, 1. In the same way, you take 4, it's going to be 1, 0, 0. Because when you do plus 1 over here, 1 plus 1 is 0. There will be a carry forward of 1 to the least significant bit. And then it's going to be 1 plus 1 again, it's going to be 0. Then there is a carry forward of 1. It's going to be 1 plus 0, which is going to be 1. Now, when you take 5, it's going to be 1, 0, 1. When you take 6, it's going to be 1, 1, 0. When you take 7, it's going to be 1, 1, 1. So you could see we already reached to the maximum number, where you could see all of those bits are represented as 1, 1, 1.